Live streaming is on.
Hi, I can see people if I switch over to the YouTube live stream, just not on Jitsi.
Well, at least we know that's working.
Is there a default way for us to retrieve the video once it has been recorded, essentially? Because like up to now, it has been quite sparse to then like someone posting the actual link to the video. So it would be nice if there was like some standard place where we post those links.
Posted the link. I just posted the link to Slack.
Cool. Is it always the same?
Well, especially not now. No.
Oh right, yeah, sure.
Yeah.
And the link, I think, will vary because every video will have a different, URL, right? But, usually it's Ben, so it will be Ben. But because these are private, you won't be able. If you click on the user, you won't see these videos, right?
Okay, I think we can get started. Does anyone have any announcements or updates they'd like to give? If so, please stick up your hand using the Jitsi raise your hand thingy. I guess I don't really have any updates worth talking about. Does anyone else have their hands up? No updates. Okay, well, I guess we'll hand over to Daiki, who's going to lead our presentation today. He's talking about a new piece of TSGit infrastructure we're hoping to add to the TSGit dev GitHub organization and website, etc., etc. So it'd be great to get people's feedback on where things are at. Over to you, Daiki.
Can I please share my screen? Can you see my screen?
Yes, we can.
Okay, thank you. So, hello, my name is Daiki, and I'm a PhD student in statistics at the University of Oxford. And today I'll be talking about TS-Trait, which is developed to simulate quantitative traits of individuals in a tree sequence. So this is going to be the summary of my presentation today. And at first, I'll be explaining the importance of tree sequence in GWAS. Then I'll be introducing the newly developed package called TS-Trait to simulate quantitative traits. And then afterwards, I'll be talking about the versatility of TS-Traits. And finally, I would like to talk about the aim of this research project. So before I start this presentation, there are two more contributors to this research project, Jerome and Herchen. And I would actually really like to express my appreciation towards their help because this TS-Trait was the first Python package that I've developed in my life. And I actually struggled with the initial steps, but they provided a lot of valuable support to me. And I think I wouldn't have been able to complete this research project without their support. And I especially would like to thank Jerome for supervising me. And I really enjoyed doing research under his supervision. So first, I would like to talk about the importance of tree sequence in GWAS. So what is GWAS? GWAS is an abbreviation of Genome-Wide Association Studies. It is one of the hottest fields in medical sciences, and it tries to detect the genetic variants that are associated with a specific trait. GWAS has successfully identified many loci that are associated with various human diseases and traits, and the results have been actively being used in human trials and clinical practices. However, there are some limitations of GWAS, and one of the limitations include demographic effects. The majority of participants in GWAS are of European populations, and polygenic risk scores suffer from reduced accuracy in non-European populations. It would be important for us to develop new tools to study the transferability of polygenic risk scores across different populations. And also, GWAS has difficulty to detect ultra-rare variants. So that's why it has been suggested that we need extremely large sample sizes, as in millions or even tens of millions, to be able to detect those ultra-rare variants. And I believe that these issues can be resolved by using tree sequences. Next, I would like to talk about the advantages of using tree sequence in GWAS. So the tree sequence format can be used to efficiently analyze and store millions of human genomic data. And this would especially be important in studies such as GWAS, which uses genetic information from millions of individuals. Also, simulation frameworks that uses the tree sequence encoding such as MS-Prime, SLIM, and STD-POPSIM can simulate genetic information of individuals given any demographic models, selection history, and mutation model. Actually, for me, this SLIM over here was the first genetic simulation framework that I've used in my life for my PhD research project, and I've incorporated a variety of demographic models inside this SLIM to be able to simulate individuals and see how mutations have changed inside individuals. So that's why using this kind of simulation framework can enable researchers in GWAS to incorporate demographic effects into their model. Also, this ARG or ancestor recombination graphs is a very, very hot field of research. Recently, a research manuscript was published to introduce ARG-needle, and they have shown that inferred ARGs can better detect more associations to ultra-rare variants than imputation, which is a widely used technique in GWAS to identify rare variants. Also, ultra-realistic genetic simulations are possible with recent advances in ARG simulation and inference techniques, and a recent paper was published to show that it would be possible for us to simulate millions of French-Canadian individuals, which would not have been possible without the usage of tree sequences. Thus, tree sequence can be used to alleviate some limitations of GWAS. Even though tree sequences can be used to resolve major limitations of GWAS, there are no methods for simulating quantitative traits from tree sequences. So there are packages to simulate genotypic information based on the tree sequence format, and there's also packages to infer the tree sequence from the actual genetic information, such as TS-Infer and ARG-needle. But there does not exist any simulator that can simulate phenotypic information from the underlying genetic information given by the tree sequence. So, since there are a lot of advantages behind using this tree sequence in GWAS, if we could implement a quantitative trait simulator, it would be possible for us to efficiently use this tree sequence format in GWAS simulations. And this would benefit the GWAS community as they can use a variety of useful packages in tree sequences and ARGs. To simulate the phenotypes, many research projects in GWAS are taking one of these methods. They're either converting a tree sequence file into a VCF file and using that VCF file to simulate the phenotypes, or they're taking a matrix-based approach, meaning that they're using some functionalities in TSKit to obtain the genetic information of individuals at a particular site and using that information to simulate the phenotypes. But it has been shown that compared with the matrix-based approach, tree-based approach are substantially faster to compute the statistics, and the advantages of using tree sequences is that we can actually use this underlying tree-based architecture instead of using the matrix-based approach to compute the statistics. So we require a tree-based approach to efficiently simulate the quantitative traits. And that is going to be the main part of my presentation. And this TS trait. And I'm planning to actually focus on quantitative traits. The quantitative traits are traits that can be expressed numerically, such as height, weight, and blood pressure, and they are the major traits inside humans. And also, these quantitative traits are very complex to analyze as they're polygenic and are affected by thousands of genes, and they're also influenced by environmental effects. Now that I've finished describing the background of this research project, I would like to talk about TS Trait, which is a newly developed package to simulate quantitative traits from a tree sequence data. This is going to be the overview of the TS Trait algorithm. And at first, it's going to be the input. So this left side over here, this over here is the Python API of the function to simulate the quantitative traits. And the input of this function are the following. We have to put the tree sequence data with the mutation, number of causal sites, trait model, narrow sense heritability, and the random seed. These will be described in detail later, but for this tree sequence, this TS trait supports quantitative simulation of tree sequence with any mutation models. So after the input is given to the function, TS trait selects the causal alleles. So TS trait chooses causal sites at random among all the sites inside the tree sequence data, and the number of causal sites that affects the trait is determined by the user of the TS trait. And when the TS trait selects a causal site, and when there are more than 2 alleles in that causal site, TS trait randomly selects a causal allele among all the alleles inside the site, and then ancestral state is not chosen to be a causal allele.
Say, Daiki, can I ask a question?
Oh, yes.
Does it does it choose the sites? It chooses polymorphic sites, and does it make the choice in a way that uses the allele frequencies at the sites?
Oh yes, so actually, that's going to so I'm planning to explain about how the effect sizes or how that little frequency comes place in the simulating effect sizes part. But for this, selecting the
No,
causal site,
Daiki, does it? Daiki, I don't think that we use the allele frequency to pick the.
Oh yes. So for the
the
picking the causal sites, we just pick it from random, and then for this effect sizes, we use the little frequency. So for this causal site, we just pick it from random, and for this causal allele, we just pick an allele from random from that site. So it does not incorporate the allele frequency when we actually choose the causal site or the causal allele inside the tree sequence data. But thank you for your question.
Well, one more question about, is this for diploid or haploid setting?
Oh, this is for, so this model actually supports both diploids and haploids. So inside the tree sequence data, there's the individual table, which describes which individuals have the particular nodes. So actually, this simulation simulates quantitative traits on each node, and then at the final step, it converts the nodes to individuals. So you can support the simulations from both haploids and diploids, and also even for individuals having multiple, more than 2 sets of chromosomes as well.
Thank you.
So after TS trait selects the causal alleles, it simulates the effect sizes. So before I explain the details of the fixed size simulation, I'd like to very briefly talk about the phenotypic model of TS traits. The TS trait simulates quantitative traits from this model over here. So in this model, this beta and epsilon are simulated, and this X is the genetic information that is obtained from the tree sequence data. And we assume that all traits are additive, meaning that there is no dominance and there's also no interactions between genes or interactions between genes and environment. And this is actually a common assumption that is used in GWAS because the meta-analysis of human traits based on all twin studies of complex traits between 1958 and 2012 have shown that most human traits are additive. So that's why currently in GWAS, almost all simulations are conducted by using this additive model. And the fixed sizes in TS trait are simulated from either trait model additive or trait model allele frequency. So this trait model additive assumes that the fixed sizes is simulated from a normal distribution where these parameters are given by the user. And this variance is divided by the number of causal sites as to make sure that the phenotype does not explode as the number of causal sites become big.
Can I ask
But
a quick question,
that-
Daichi? Just
Mhm.
about the previous one with the correlations between the environment and genetics. So presumably you don't allow there to be sort of non-causal correlations. So you might expect, for example, in humans, there are populations in Africa that all have a particular particular suite of genetic variants, but are exposed to a common environmental background as well, which is not a G by E, not an obvious G by E interaction. It's just caused by geography, as it were. Presumably, that's not incorporated.
Oh, so yeah. So we haven't implemented those kind of things inside the simulation model, especially because so currently actually analyzing those kind of like environmental effects can be pretty challenging. So as I did some background reading on how people have actually used the simulations to incorporate demographic effects, they have actually just simulated individuals from like African ancestries or European ancestries, and so which genes are different, and so how GWAS can detect them. And actually, a lot of them have not really incorporated the environmental effects, especially because it's very hard to actually analyze how the environmental effects are actually influencing the genotype.
Thanks.
But Jan, if I think what you're asking is, one allele is present just in Africa, not elsewhere, right? So that will be part of the tree sequence already.
Exactly. So if you've got if you've evolved the tree sequence under some demography, then you're likely to have geographical separation in that demography, and you're likely to have correlations of environmental effects that are not really G by E interactions, but are just caused by the demography, essentially.
But that's part of the tree sequence already, and if that side is a causal, it will just you'll just see the effect there because elsewhere you don't have it. Yeah.
So I thought you were asking if we could simulate environmental noise that was sort of grouped by individuals, Jan, or geography.
Yeah, essentially. So whether you could that would cause a correlation between the genetic variants and the environment, but only through demography. So if you said, you did your simulation and it was an out of Africa thing, but then you said all the Africans in your simulation, you were exposed to more sun or whatever, or high levels of vitamin D or some environmental effect that pushed them all up by a certain amount, then you would see a correlation between the environmental effect and the some of the genetic variants that were at higher or lower prevalence in Africa. But it's not an obvious G by E thing. It's just
you could do that by allowing the user to give you a covariance matrix for the epsilon.
Right. Yeah. Good point.
But yeah, I think that could be very important because that's one of the main things that GWAS has got to worry about.
So the way we handle this, for example, in AlphaSimR is we simulate the genetic values, right? Just the XB component. You can do also phenotypes on top of that. But then the user is allowed to add additional effects, right? You know, you have males versus females, you have Africa versus that environment, etc. Yeah, maybe that's.
Yeah, I was
what
just
you
about
can-
to say the same. We could add like functionality to add like another vector of noise on top of that, which is currently not in place, but that should be straightforward to implement.
Daiki, just one more technical question. Shouldn't the mu also be divided by m?
Oh, actually, over here, as I read some papers, I actually agree with that, but a lot of papers actually just incorporated this mu inside, and they've only divided by this m. And actually, when they actually simulate the effect sizes to see how it affects, a lot of people are actually incorporating this mu to be 0. But some were actually incorporating like 1 or 2, but they weren't actually dividing it by m. But if users want to divide it by m, they can just put it inside the function. But thank you very much for your suggestion.
So following up on the last point as well, I mean, there's no reason that users can't add noise themselves onto the result. And possibly that's something that we should, you know, document an example of doing, because you know there's a lot of flexibility in having this as you know, being implemented in Python, and I guess that's quite a useful thing.
Oh, okay, thank you. Actually, as the output, we can actually obtain those individual IDs. So I'm thinking that maybe people can just simply use those individual IDs to examine and then use the original pre-sequence data to maybe obtain those like other information and then incorporate it as well. Then but thank you very much for the suggestion. And in addition to this trait model additive, this TS trait also supports the simulation from this trait model allele frequency. So in the previous model, we have assumed that the fixed sizes of each site are all the same, but actually studies have shown that rare variants have increased the fixed sizes from common variants, and it is widely believed that this is due to negative selection. So that's why we have implemented the frequency-dependent model like this, as indicated in these papers over here. And this alpha parameter over here determines the weight of the rare variant. So if this alpha value is a negative value, it means that the effect sizes will be larger for those rare variants. And this frequency-dependent model described over here is widely used in GWAS simulation. And the parameters of the fixed size simulation. Oh yes.
Mikey, that P1 minus P thing there is presumably assuming that you haven't polarized the allele frequency, so you don't know whether, you know, a very high frequency is because, well, you see what I mean, that you don't know which is the ancestral and derived. But if you of course you do know in a tree sequence, don't you? So you could take that into account. You could have a sort of polarized version, couldn't you?
This actually P is coming from this P is actually the causal allele frequency. So this is frequency of the causal allele. And sorry, can you please describe what polarized means?
Well, it's just that you tend to use P times 1 minus P, because then when P is at an intermediate frequency, you have the highest value. And when it's at a low frequency on either side, you've got a low value. And that's because quite often you don't know which is ancestral or derived, I think. But because you do here, then it might be that there's a different function in there that you could use. That was my thought. But don't worry about it. I'll talk about it later.
Okay, thank you, Jan. So these parameters of the fixed size simulations, this mu, sigma, and alpha, are given to TS trait when users specify the trait model. So for example, for this trait model additive, they can put this trait model mean, trait SD, and for this trait model allele frequency, they can put these parameters and alpha inside. Then they specify the trait model in this TS trait implementation. The relationship between alpha and effect sizes are shown in these plots over here. So for example, in the trait model additive, there is no relationship between this allele frequency and effect size. But as the value of alpha decreases, the emphasis placed on the where variants increase. So they have increased effect sizes compared with the other variants. And this is obtained from the simulated effect sizes from MS Prime simulated tree sequences. So after the effect sizes are being simulated, we obtain the genetic values of individuals. So the genetic values can be computed by this x times beta, and this beta is the effect size that has been simulated. So we need to obtain this x, which defines the number of causal alleles that the individuals have. So we have implemented a tree traversal algorithm to determine the number of causal mutations that the individuals have, and this function is speeded up through number. So as shown in this diagram over here, for allele frequency or for these kind of like population genetic statistics, we can directly use this underlying tree structure of the tree sequence to determine those statistics. And this tree traversal algorithm is used for all nodes that have the causal mutation. So I've indicated an example over here. So let's say that there is an example tree sequence data like this, and let's suppose that there mutation 0 and mutation 3 are causal at this site. In this case, there'll be two tree traversal algorithms running at this site to capture the individuals for both mutations. So the first algorithm starts from node 11, which is the node of mutation 0, and then as it goes down, the algorithm stops at node 9 as it has a mutation, and even though it passes through node 4, it is not counted as it has a mutation over here. And a similar thing is formed the second mutation. And from these steps over here, it seems that node 3, node 6, and node 7 have causal mutations at this site. So that's how we can obtain which individuals have the causal mutation. And after this individual information is obtained, the genetic values of individuals are determined by simply adding the simulated effect sizes to the individuals that have the causal allele. And this tree traversal algorithm is actually validated by using unit tests of various complex tree sequences and mutation structure. So I'm pretty sure that the algorithm is in fact correct. After the genetic values are obtained, we'll be simulating the environmental noise. The environmental noise in TS trait is determined by this Breed's equation over here. So this narrow sense heritability is inputted by the user, and this additive genetic variance is computed from the simulated genetic values. And considering that since we have the additive model, which means that the total phenotypic variance is a simple sum of additive genetic variance and the environmental variance. The environmental noise is simulated from this normal distribution over here. And after the environmental noise are being simulated, phenotypes are determined by simply adding the genetic values and the environmental noise. And these plots are obtained from the quantitative trait simulation by using TS trait, and they represent the relationship between the narrow sense heritability and environmental noise. So when the narrow sense heritability is said to be a low number, the variance of the environmental noise is pretty large, but when the narrow sense heritability is said to be a large number, the variance of the environmental noise will be smaller compared to the phenotypic variance.
Daiki, I just suddenly thought if as Jerome suggested, or was it Herchan, that you allowed people to add noise of various sorts to the data, then obviously it would change this. So it would be hard to, you wouldn't have the same narrow sense heritability, right? Because you'd have a bigger denominator because you'd be adding extra variation somehow. So, so given that the user inputs the h squared, is that right? Then it would be quite difficult to work out how you would input the right sort of variation, you know, structured by individual or something to maintain the same h squared. But
well, actually, even for that part, I think the simulations can be easy, can be pretty simple, especially because for this additive genetic variance, what we did is that instead of, we just computed this variance of x times beta, where beta is the simulated genetic effects sizes. So this x beta is actually representing the simulated genetic values. So I think we can simply just plus some variance terms, plus some terms over here, and compute that variance, and then multiply by this to determine this environmental noise.
Okay, thanks.
Sorry, thank you. Well, thank you for your question.
But Jan, also what one could do is you just say, you know, heritability equals 1, so you only get out genetic values, and then you can add any amount of noise you want to.
Yeah, that's true. You could just tell it not to put any variation, environmental noise on at this point and add it later.
Oh, thank you very much for your feedback. And then for the final output, so this is a very simple implementation of TS trait. So from the simulated tree sequence data over here, we put this trait model inside this model part. We put this tree sequence over here, and then the simulated result over here is actually a data class that contains two data classes to describe the phenotypes and the genotypes. So the phenotype information can be obtained by using this dot phenotype. So there's individual IDs, phenotypes, environmental noise, and genetic values, and these values inside these arrays aligned based on the individual IDs. So for example, this 0.53, this part corresponds to individual ID 0, for example. And the genotype information can also be obtained by using this dot genotype, and it has this causal site ID, causal allele, effect sizes, and causal allele frequency. And these values in these arrays are aligned based on the site IDs. And now that I have explained the details of TS trait, I'll be explaining the versatility of TS trait. So these plots show the computational time of TS trait. The first plot over here shows how the number of individuals influence the computational time. So this plot indicates that the realistic simulations of 1 million individuals can be performed within a few seconds. So it's very fast. And the second plot over here shows how the number of causal sites influence the simulation speed. So in this case over here, I've used simulated French-Canadian dataset and also the inferred tree sequence of the 1000 Genomes project. So these plots show the simulated phenotype, simulated genetic values, and the simulated environmental noise from the French-Canadian dataset. So even though it includes 2.7 million individuals with 1,000 causal sites, the simulation speed was less than a minute to obtain these information, making it to be very fast. And also, I've compared TS trait with the previous study proposed by this research paper over here. And since TS trait actually uses the tree structure inside the tree sequence dataset, it can simulate the quantitative traits at 20 to 30 times faster compared with the technique developed in the previous paper, even though TS trait supports more complex trait models. And I would also like to very briefly talk about unit tests and statistical tests. So that all the input errors are captured in TS_trait, and also unit tests are used for all functions inside TS_trait to examine if they can detect the correct errors, have the correct output dimensions, have the correct properties. And for the unit tests, I use unit tests to examine the properties of functions in these special cases, such as individuals having internal noise, individuals with multiple noise, individuals with non-consecutive noise, multiple mutations in a signal age, reverse mutations. And for all of these cases, TS_trait performed perfectly well. And I've also used statistical tests to examine if the simulated values are actually have the desired distributions. And I've actually created a variety of tree sequence data with complex mutations in tree structure. And as we can see from this QQ plot, the distribution works totally fine, as expected. So finally, I would like to end this presentation by talking about the next steps of this research project. So I've actually created a full documentation with worked examples for this TS_trait, and I hope that I can very briefly show it right now. Oh, so this is the manual that we've created, and these links are working. So, for example, for this welcome page, I put these links for the tree sequence tutorials, MS Prime manual, and the TS_kit tutorials, and also these are the contents. So first is installing TS_trait. I put these instructions of how we can install TS_trait. The next is quick start with all of these worked examples with these visuals over here. And also, I've put this phenotype model, this output of the phenotype, and then this shows the phenotype output. And for example, when I click these links, it shows you which classes it corresponds to or which functions it corresponds to. And then it also shows the genotype output, the narrow sense heritability, and I put some examples of some narrow sense heritability. And then I've also described the additive, the trait model. So this supports two trait models like this. And then for each of these models, I put examples with some visuals to show how the simulation is being conducted. And also for the Python API, I put the Python API for all the classes and functions that the users have to use. And then it obviously shows the source code. It has the parameters and what it returns, with all of these links to the documentation such that the readers can refer to what this function is. And then also, since I have the documentation, I hope that I can put this TS_trait documentation under the tskit.dev, publish this TS_trait as a Python package, and submit this manuscript to Bioinformatics Applications Notes. And actually, for me, I started my PhD research project by using Slim. And people in the Slim forum always promptly answered my questions. And at that time, I always thought that I wanted to actually participate in the community as well. And I really hope that this TS_trait can actually be part of the TS_kit community. And I'll be very excited if I could make some contributions to the TS_kit community. And also, I would like to very briefly summarize the importance of this TS_trait. So in the TS_kit community, there are lots of very useful packages, such as like MS Prime, Slim, TS_date, TS_infer, and all of these kind of various packages. And they support a lot of complex simulations, complex inference of ARGs and tree sequences. And I believe that if we can add this quantitative trait simulation aspect inside this TS_kit community, I believe that this can greatly benefit the GWAS community as well, as they can use these TS_kit community packages to supplement the research project to be able to solve some limitations of GWAS. So finally, I would like to thank Jerome for supervising this research project and having weekly conversations with me. I would like to thank Herchen for always providing me a lot of valuable advice, Jerome's group members for supporting my research project in the weekly group meetings, and Alison for becoming my primary supervisor and supporting my PhD research project, Alison's group members and people in the statistics department for always giving me advice regarding the research projects and having valuable conversations with me about the research projects. And thank you very much for listening. And I hope you enjoyed this presentation. Do you have any questions?
Go ahead, Gregor, I think.
Oh, sorry. Yeah.
Thank you.
Well done, Daiki. Can you
thank
say a
you.
little bit more about the algorithm? So if I understand correctly, right, you start at the root and you go down, right? And then you accumulate the effective mutations for each branch, and then whatever samples are below that branch, they get that value. Is that correct?
Oh yes. So for this algorithm over here, at first we find out where the causal allele is located inside the tree sequence, and then we traverse down. So it is a simple traversing algorithm to find out leaf nodes, but the algorithm stops when there is a mutation. And we do this for all the causal alleles inside that
You mean a
particular
mutation
site.
at the same site, right? You stop when you hit
Oh yes,
them at
inside the site.
Yeah.
Oh yes, so this is mutations inside the same site.
So think about a site that has a lot of mutations, Gregor.
Yeah.
This is kind of working in the complicated loads
Yeah.
of mutations case.
Yeah. Okay, so then are you traversing then the mutations table effectively along with the edges, or I'm just trying to think with the data structure how this works. But maybe I can look at the code. Yeah.
Oh, there you go. Thank you.
We're
Oh, yes, so-
actually navigating to like the particular tree at the site of that mutation, and then doing a simple tree traversal algorithm for the subtree that has the mutation above it.
And then you accumulate the value in where? Because you kind of have to accumulate, right?
Well, then for each leaf, you have an array that is the length of all the leaves essentially, and then you accumulate those values
Okay.
once you hit the leaf.
Okay. Yeah. Thank you.
So it's big O(n), Gregor. I mean, it's just a fast big O(n), you know.
Sure.
Well, thank you very much for your feedback.
Can I ask something, or was Peter first? I can't remember.
You were.
Okay. Have you thought about how you might cope with missing data? So what happens if? Yeah.
I actually haven't implemented the missing data inside the simulation algorithm because I actually hoped that this could be used for actually simulating traits from simulated genotypic information and also from the inferred information. So I haven't actually incorporated those missing data inside this algorithm.
Because if you could think about how to do missing data, then you could try and infer variation on traits of ancestors in the tree sequence.
Hold on, Jan. What kind of missing data are you talking about?
Sorry, I mean missing genotype data. So if like in this example, node 3 didn't have a branch going to it at all, then essentially you don't know what allele node 3 carries at that site, and therefore it might affect the value in some way. I don't know. It would change the variance of the expectation of what the phenotype was or something. But you could, it'd be quite interesting to take in the example that Daiki has here. Could you, for some of the genome, what node 12 has as a genotype, and node 12 is an ancestor, and node 12 has some sort of phenotype. Can you assess what that phenotype is in any way?
Oh, okay. So do you mean that simulate the phenotypic? So let's say that node 3 is unavailable, and let's say that we can simulate the phenotypic information of node 12. And are you saying that whether we can simulate this the phenotypic information of node 3 or not?
No, it's more that if you look at node 12, for instance, that node was an ancestor and it had a particular phenotype, but node 12 might not be present in all the trees. You might only have some information in certain portions of the genome about node 12. So I just wondered if it's how maybe it just comes out in the wash and everything you just average it out or something. I don't know, but
Can I just jump in,
Okay.
because with Peter we had at some point on GitHub somewhere did this discussion, right? Some ancestors are not, you don't have the full chromosome, for example, right?
Yeah.
Let's say you only have a half, and it will only have the half of the genetic value you could have, right?
exactly.
That's an important thing, sort of, right? Conceptually. Yeah.
So I guess we're only
Maybe I
thinking
can
about samples, right?
Mhm.
Here.
Yeah.
Yeah.
Ancestors is a different story.
But if you, for example, you flagged up node 12 as now a sample, then it would just be like a sample with lots of missing stuff. It'd be like having a node 3 where you had thrown away a load of the topology leading to node 3. So you could still have it as a sample, but it turns out into a missing data problem, right?
But you've
That might be
you've simulated the mutations on branches, yeah. I mean,
Mm-hmm.
I'm not sure there's any actual information here.
Right, but if you detach node 3 at this particular site, say you've got a whole set of trees between 0 and 100, and between 0 and 1 you've got what Daiki has shown here, then you could detach node 3, and that means you don't know what value node 3 has at the genomic position 0. So what does that mean in terms of its phenotype? That's all I'm asking.
Okay, well, I think that's a that's a big question that we don't really know. It's not a feature to add to the, like, in terms of missing data. The simplest, like, for all the simulations that we have, the tree is either there or it's not, where we're not actually doing missing samples in any current
Right.
inference or simulation. So, until that's in place.
Yeah. No, I'm not saying it should be added. I'm just saying it's something to think about for in the future, particularly because of these ancestors, right? It is interesting to know, as Gregor said, what the phenotype of ancestors is, given that you only have partial genetic information about them.
I have a brief suggestion is that you might think about making it easy for people to use a t-distribution as well as a normal, because because then you'll get, by adjusting the degrees of freedom, you can get, something that has a few big mutations and then lots of little ones. I don't know if Gregor might know other ways people do that. And I also had a question, which is, like, if I think about doing this in practice, it seems like, since an awful lot of sites are something like singletons or at low frequency, like, it seems like maybe a lot of the heritability will be like explained by very low frequency things, which we would have trouble in practice finding. And so that the inferred heritability that somebody would get by, doing GWAS would end up being a fair bit lower than the heritability you put in or something. But have you looked at this, or have you thought about this?
Actually, so that's why for the number of causal sites, we set it to a very large number, such as, for example, a lot of research studies are taking thousands or even tens of thousands, or let's say some research projects are even taking like 20% of causal sites, so that they have enough number of causal sites to select from. Because let's say, for example, if we just select like 1 or 2 causal sites, it's true that we might just take those ultra rare causal sites. So that's why if the user were to implement this, they would have to implement, they would have to have the number of causal sites to be fairly large, so that it can select a variety of different sites inside the tree sequence.
Is that a good model, Gregor? Like, or should we make it, easier to choose your causal sites more cleverly?
I mean, that's the holy grail, right? If we would know the causal sites, right, we wouldn't be searching
okay.
for them, right? So nobody really knows, right? Quite often, if you do something very complex, if you choose them at random, you're probably fine to begin with. Later on, one might start to impose. So maybe thinking in terms of, can a user bring in information, right? So at the moment you choose them at random, could you allow the user to specify what the sites could be, causal sites?
Or provide like a mask of where the coding
Something
sequence
like that.
is and choose them randomly there.
Stuff like that, yeah. And just to add to the t-distribution, people sometimes use gamma. That in some populations seems to be fitting well.
But
the
that's
estimate
just
effect.
positive then.
Yeah, and you flip the order, you flip the sign randomly, yeah.
Oh,
Okay, thank you.
I mean, quite often when you estimate this from the data, you don't have the sites polarized. So, you're kind of estimating, absolute effect. You quite often, if you look at the distribution of absolute effect, it looks like a gamma distribution. If you have the sites polarized, alleles polarized, then it's easier, right?
Mm.
Specific to
you.
this, you said for the multi-allelic sites, maybe. So at the moment you just pick one allele being causal, right? Which I believe means that the ancestral allele has no effect. The mutation from that allele has an effect. And really what you're simulating is the allele substitution effect. When you have multiple alleles, maybe, a richer model could be to have allele substitution effects between all pairs of alleles.
Okay.
Right, because biologically, think about if this being a protein, mutating from A to C could be different than A to G, and and other combinations. With the mutations table, I think that's quite easy to do, actually, potentially.
Gregor, is there literature on that, like on those kind of reversal things? Because I mean, would it then be like, say, A to G is plus 0.5 and then G to A minus 0.5, or how does that work?
Not to my understanding, there's no literature, because at the moment nobody can estimate that, because without the tree sequence, you're not really seeing, which mutation goes to which, right? And that's why we're kind of also focusing a little bit on the biallelic sites mostly. Yeah, but maybe this is something for the future. So yeah.
So it'd be good to it would be good to kind of have these sort of things in mind with the API, so that we have the flexibility to add these sort of richer models. So I guess a good thing, a super helpful thing would be to sort of outline what these nice features for the future would be, and then we're not sort of painting ourselves into a corner with the current API. So really great to get your everyone's thoughts on what these features should be and how they would build onto the current API. That would be extremely helpful.
You might look at we might talk about the API the standard PopSim has for specifying distributions of fitness effects. It's, not ideal probably and not the same thing, but has some similarities.
Can you divorce the environmental variation from the genetic one? So can you do a simulation, keep the same, all the causal variants and everything the same, and the effect sizes, and then just throw different amounts of environmental variants onto it to take the environmental variants away and then throw it in a different way, or stuff like that?
Oh yes, actually, adding the environmental noise is very simple. So it just simulates from this full distribution over here. So actually, for this algorithm, the most time-consuming part, or the most difficult part, is actually this tree traversal algorithm.
Yeah, so
And this one
Daiki, with the
can be done very
API, are the two bits separate in the API? So can you do the genetic stuff, simulate it all, get the effect size and all that sort of stuff, and then afterwards you get something on which you can then impose extra genetic variants, and then take a different set of random environmental components and use them instead. I don't know what the API is.
Oh, okay.
I think the answer here is that we currently haven't exposed that bit of the API, but it's obviously all there. I mean, the workflow we take could be exposed completely, and then people could do that as well.
I don't know. Maybe Gregor would know whether that's something people do, whether they treat the environmental component completely separately, such that you can repeat that multiple times for the same genetic component or stuff like that. I don't know. Or the other way around.
It's very simple, right? It's just if we set heritability to 1, your trait will be purely genetic, right? No environmental effect. And then you just need to add a different epsilon yourself. And just in terms of API, Daiki, if you can sort of make it such that it's easy to add a different vector or vectors, or then I think that then will pretty much cover all the use cases. Yeah.
Oh, okay. I think
as Jerome said, if we come up with a good example that does that, like where people do you add some custom environmental noise based on geography, for example, then that would be very clear on how to tackle that.
Or males versus females and stuff like that.
Yeah.
Yeah, and where you do that repeatedly for different environmental noises for the same genetic simulation, I can imagine that being a useful thing.
So maybe a nice case could be, right? Allocate sex. Roughly half will be males and half will be female, and you wouldn't expect that they would differ, across different environments. But then maybe if you have a certain tree sequence simulation where you kind of have 2 subpopulations, and you could then, add a, I don't know, a difference of 5 units between one versus the other subpopulation, something like that. Yeah.
And I guess you might
this is as an example, yeah.
You might also want to do the reverse, where you know what the environmental component is, and then you re-simulate the genetics, but use the same environmental component.
So we're at the hour, so we should probably finish up. So thanks very much, Daiki. That was a really great presentation.
Thank you very much.
Yeah, this looks excellent.
Is everybody happy for us to sort of make this a native TSKit dev package and put it up on the website and all that? Everyone's happy? Great. Okay. Thanks, everyone.
So next week we have Herchen, and then we'll be having a summer hiatus of meetings after that.
Do you mean next week, or do you mean the one after?
Sorry, I mean 2 weeks' time. It'll be the next meeting. Will be Herchen talking
next week in 2 weeks' time.
Yeah. The next meeting will be Herchen talking about new features for additional nodes in MS Prime, and then we'll be on summer break for a couple of months, I guess.
Great. Thanks, everyone. See you all later.
Thanks.
Thank you.